Next up, we have Yuri from Uber. You'll see a sort of a theme between Helga's talk and Yuri's talk with kind of now an Uber twist on the area. Go ahead, Yuri. Thank you.
All right. Thanks, everyone. I hope you're enjoying the talks. I will try to continue the theme that so far has been already discussed. So Ben mentioned that deep systems are really the things that we're dealing with today, and they require a certain new kind of tools to operate them and control them. As you can see from the title of my talk, I'm trying to make a point that these systems are not just deep, they reach the point that they become incomprehensible for mere humans. And as an example, I'm sure not a single engineer at Uber knows what the whole architecture looks like, what every service is doing. It's just impossible, not only because it's so complex, but it changes every day. Like tomorrow you have more dependencies between your services you didn't even know about. So nonetheless, we do need to operate them, these systems, because and we need to operate them reliably, because that's what our users are demanding. And if you are stuck in a bad neighborhood at night, you don't want your ride-sharing app suddenly to show, sorry, we're down for maintenance or something, right? And this is the things that I surprisingly still see on some of the websites, even on the banking sites. It's kind of a sad thing. I mean, most like internet companies don't do that, but nonetheless, we are not infallible. Outages do happen. Like in this example, I have like a list of outages that happened just in 1 month this summer to very high-profile companies, and the outages themselves were pretty high-profile. They lasted several hours. They affected lots of users. When these things happen, we do need tools to be able to mitigate these outages as soon as possible, because this is really one of the most important job of a person on call or the first responders, is find a way how to mitigate an outage, because, well, hopefully in many cases our system are resilient enough that it will auto-correct, but if it's not, then we need humans to jump in and figure out what's going on. And once we start dealing with these deep, complex systems, then figuring that out is actually very hard, because there are so many dimensions that can get affected. And that's why we're at this conference actually talking about observability, because that's what provides us the ability to understand what's going on in the systems and try to correct them. As an agenda, I will do a brief introduction to distributed tracing, to the mechanics of it, because I don't know if everyone in the room is actually familiar. We've been talking a lot already about tracing, but what it does, right? So it's kind of a basic introduction. And then I will talk about some of the tools that we built at Uber that are specifically focused on this problem of how do you resolve the outage as fast as possible? How do you find what's wrong in the architecture? So about myself, I've been at Uber for 4 years. I work in the reliability platforms. I started the Jaeger project, which is our open source tracing system. It's part of the Cloud Native Foundation. I also work on OpenTelemetry and OpenTracing, and OpenTelemetry is a new exciting project for getting standardized telemetry out of your application. So what Ben mentioned is like the 3 data pipes that you need to have in place before you can have any observability in the system. And just a fun fact, I wrote a book on tracing, so I'm kind of a self-proclaimed tracing expert because of that. You can find it on my website. When I started tracing, there was no real information about how not what it does, but how you actually roll out tracing in a big organization. And that's primarily what the book is about: how you start, where you start, and what you need to do. The main reason why I think dealing with outages in these complex, deep systems is very challenging is because there are so many failure modes, right? Every connection between services introduces a new potential point of break. Plus, the microservices architecture encourages us to use polyglot systems, like services written in multiple languages, and so that just increases the number of dimensions where things can go wrong. And so we need tools to kind of deal with that situation. right? And this is an example of a service diagram for Uber. It's an old one, actually, a couple years ago. And it's not the whole of it, it's just part of it, right? But the point here is that that's already like beyond complex that anyone can really understand. And it changes every day, right? And so like transactions can hit dozens of services within that architecture when something happens. And the interesting part is that when we talk about analyzing problems or even performance or outage problems, and we say, well, let's look at a transaction. The problem is you don't even know sometimes what the transaction is, right? Because the reason we know about an outage is because there is some business metric that starts failing. Right. For example, we can have a metric at Uber saying for a particular city there is supposed to be a certain number of rides going every minute, right? And if that metric drops, well, that's an alert. It's very easy to set up an alert of that kind. But how do you go from that alert to figuring out, well, then what happened actually, right? Because it could be that, I don't know, maybe there is an increased latency as in the previous talk, some degradation in performance, and people are just not like actually taking the ride because it takes too long, right? Could be that. Or it could be there is some bug in the code which calculates the fares and we're suddenly showing them like twice the amount of fares and they say, no, I'm going to take that ride. Or maybe the matching with the driver never happens. There are so many things that can actually break. But all you had is an alert saying, well, we don't get enough rides, right? And so, and that's what I'm trying to talk about. How do you go from that high level business metrics into what actually happened in the architecture that broke that thing? And I think this is the point that was made on Twitter several times, is that finding in this complex system, finding what broke and where is sometimes much harder than figuring out why that broke. And broke is like why I'm using it as a general. It could be like slow, it could be errors, or it could be something didn't happen, which is like one of the hardest problems to address, right? But once you narrow it down, it's actually not that hard to figure out sometimes. And so that's kind of what observability allows us, right? And but observability, as Ben mentioned, it's a property of the system, how well you can infer things, and it's our ability to ask questions and get answers from the system. Because if we already knew answers or like questions to ask up front, like with the metric use case, then well, we wouldn't need necessarily that kind of level of observability, investigative power, but when we investigate in an outage, we have a number of questions that we want to ask. And like the first one is what specifically is wrong, right? What is the symptom of that alert that's affecting users? Is it just like something slow or something errors popping up on the screen or whatever? And the second one is then we really dig down into the architecture and trying to find out, well, where that thing is happening and causing it. And finally, the last step is why. But if we're in the business of just mitigating an outage, the why is generally not that important, because once we find out where, we usually can find ways to mitigate it, right? When we route traffic to another place or something like that, or roll back the code version, although that kind of goes into why somewhat. And so the first two questions are kind of one of the most difficult ones. And distributed tracing of all the monitoring observability tools, this is kind of in a unique position because it can tell us the answer to these first questions, like what and where, and it accelerates the whole outage resolution. So just as in an intro to the tracing itself, so let's say we have some architecture. That is just like a demo example, hipster shop. And when we say we have observability, that means we just like all our services are recording tons of events, like potentially every service emitting millions of events per second about what it's doing, right? So is that observability, is that enough? The answer is no, it's not enough, because if you are trying to understand how this whole system works in tandem, when you have multiple services cooperating, then just having a stream of events doesn't tell you that much, especially because like if you imagine Uber as a business, we have like 1,000 cities, and the difference in populations in those cities could be like by several orders of magnitude. So if we're just looking at particular events as a time series, then a drop in any particular metric in one city may not even show in the metrics, right? So we really need to be able to drill down on various dimensions, and we need to correlate those events because they go across multiple services, and that's what we really want to track. So we want to group the events that correspond to specific transactions, and then look at them in a sort of a timeline view. And that's what tracing does, basically, right? It's the fundamental feature of tracing is that rather than looking at a single node in architecture, it looks at the transactions crossing multiple nodes. And the way it does it is actually deceptively simple, right? We have a notion of a context, which is really we assign a request ID, some unique ID to request, and we pass that ID throughout the call graph, right? It can be as simple as that. It's not, but theoretically it is, right? And while we're doing that, we can also collect all kind of performance data, saying like what metadata happened in those requests, what timing was, and we can reconstruct later in offline the whole execution, the whole path of that request, and figure out that's what actually happened in architecture. So that's tracing in a nutshell. And so I will give a few screenshots that we already saw in the previous talk as one of the top view in Helda's presentation, which is the very classic view of tracing as a single, like a timeline chart. And so that looks like this. I will just step through quickly for some of the sections here. So on the left, we see there's like a hierarchy of call, very simple, like a service and what operation that service is executing and in which order. Horizontally, we have a timeline, so how long it took. Above that, there is a mini-map that can just use for navigation easier, because when the trace is very large, you can have like 1,000 rows. You can't really see that, but in a mini-map, you see the whole thing. One of the sorry, the slides froze. One of the kind of nice features of this timeline view is that you can immediately see performance problems, right? For example, here you can see there's a blocking transactions on the database that takes like 2/3 of the execution time. So if we were to optimize that, that's the first thing we want to do, right? Another one is kind of a set of executions which can potentially be parallelized rather than doing sequentially. So again, this is a more performance-related thing. There's like this view was really invented originally for performance optimizations, not so much for root cause analysis that I will talk to you later. And it also gives us like signals when something goes wrong in that trace, so it can highlight and allow us to navigate to a particular place and like trace down from the root of the transaction where errors started to happen and what was the original source of that error. And traces are also kind of an interesting thing. So there was a question about like logs versus traces. Traces on one hand provide you a macro view of your system because you see all the services participated in a transaction, but they also provide you a very micro view of every operation that every given service was doing within that transaction. So that's what typically logs are doing. But you can actually shift your logs into traces as long as you correlate them with a trace ID, right? And this is an example of a single operation which you can see can contain a lot of rich details, like what SQL query was executed, what some other events can happen. So this simple view provides you very rich details about what the story of that transaction really was in the architecture. I often get this question from people saying, okay, well, these are all RPCs, and like Dapper originally was talking about RPC case as well. It's like, what about message-driven systems? And can we trace them? And the answer is yes, with a caveat. The caveat is that, unfortunately, I forgot to include the slide, but Professor Farnsworth in Futurama said, like, everything is possible if you can imagine it, right? And so if you can imagine what a transaction looks like in your messaging system, then you can trace it, right? And here's an example. So this is in my book. I had a chapter about specifically like a Kafka-based system. So it's an online chat application, very simple. You can type something. You can also type /Giphy and some search term, and it will pop up some obnoxious image from Giphy.com. The architecture of it is based on Kafka. So you have an API service which writes all the messages to Kafka, and then there's a storage service which picks up data from Kafka, writes it to Redis, and then there is a Giphy service which enriches the messages with some image information, right? So very straightforward. So because, again, transaction is very clear in this mental model of the transaction is very clear in the system, we can easily trace it. You just like encode the context in your Kafka messages in addition to RPC calls, and you're done. And this is an example of that trace, where you can see, for example, at the top there's a chat API service send a message. So we see a span for a message being sent, right? And then we see 2 more spans for a message being received by 2 services, a storage service and a Giphy service. And so that again, that gives you a very clear overview of what happened with the transaction, how long things took, if there are any errors or if there are some missing pieces. So yes, you can trace messaging-based applications, but as you start getting into more complex data processing pipelines, when aggregations of messages happens, then when the tracing starts to be tricky because the mental model of transaction doesn't work anymore in that case. So as great as this is, there is a bunch of challenges specifically for the purposes of what I'm trying to do here. And one of that is trace is just a single transaction. It could be an anomaly, as we mentioned. And the other thing that specifically is evident at Uber is that a given trace could be exceptionally complex. Right? The trace I showed was pretty simple, but here's an example of a real production request as a call graph, because as a Gantt chart, it doesn't, you can't even display it. So there are 30 microservices, over 100 RPC requests. That's just a transaction that happens all the time from the mobile app, right? And so figuring out what's going on in that is pretty hard. And that's not even the most complex one. Here's heat maps of sizes of traces that we collect over time, right? So we can see that the high, orange color indicates the more frequency. So smaller traces are more frequent, but we can see traces going up to 500K spans. And there is even one above 8 million spans. So imagine the trace of 8 million data points. How are you going to visualize it? What are you going to do with it? And that's why we realized that we need some other types of visualization that we want to use for these purposes. So we tried a few of them. One of those, as I showed, the graph, call graph. Another one is a latency heat map overlaid on top of that graph, right? So that's kind of interesting already, because if you're trying to get a sense of the latency in that trace, this gives you immediate answer where the path is, right? So you don't need to look at which spans is wider, or again, on a Gantt chart, it's pretty hard. However, that's still not good enough, because really when we analyze in performance, it's best to look at 2 data points rather than 1. You always take a profile at before, profile after, and you compare that, right? And so that's what the direction that we went in, and we started doing a comparison of traces. The first one is just a structural comparison. And when you're doing the comparison, we treat it as a code diff. So you have red color missing, green color, something new added, right? So 2 traces left and right. And we can see that the gray colors represent a common structure in the call graph. Then we have a bunch of red nodes, meaning they're missing on the left side, and some of them are lightly colored, because this graph is actually not the full call graph. It's aggregated in somewhat where repeated calls between 2 services are collapsed. Otherwise, it's going to be too large. And so when we aggregate them, there are certain statistics, and that there might be differences in those statistics, not necessarily structural differences, but just numerical one. That's the light colors. And finally, the main benefit of this view is that if you look at that, you immediately look at the red section. You know this is where things went wrong. This is where you want to focus to. And that's kind of really the reason why the color coding and this type of visualization works pretty well if you try to root cause a problem with that trace. In this case, you can also link because the traces are still fully available, it's just like a visualization style, we can just link it direct into the actual timeline view and drill down if we need to, if you already discovered some issue structurally in these differences. There's a issue we had about 2 years ago where we were migrating a bunch of services from one zone to another. And zones were very close, a couple milliseconds away from each other, so we were not expecting any latency impact. But instead, we saw latency almost double, and we were trying to investigate, and it was very hard given our tooling. And so that's why we built this other tool. Okay, I think my slide got out of sync. So if we try to compare the 2 traces, one is longer, one is shorter, using the previous structural comparison, it's not very helpful. For example, we can see that there are a lot of common nodes common structure. There is also some new, this tells you like the left trace is 2 seconds, the other one is 4 seconds, right? And so there is some structural differences, a few nodes on the right side. But we can't really tell from this view, is the latency overall, like doubling of the latency, responsible? What's responsible for that? Is it just like these new nodes, or maybe it's all dispersed across the whole thing? And so again, the answer is heat maps, right? Just on the graphs. Once we do that, then the answer becomes quite apparent. You can compare two traces and color code instead of like actual structural differences. We color code by latency of the nodes, and then you can see right away what happens. There's like the gray color represents things that are like the same essentially, and there's a white node saying, well, there's like a whole section of nodes which didn't occur in the first trace, so we don't know how to compare. That's why they're sort of, but that doesn't really matter, because if you look at the red trail, we can see that it's like not even reaching that point, right? And we can see that like one of particular nodes is responsible for what, like 37% of overall latency of that request. So the very useful visualization for that purpose. To finish that production story, what turns out to be is that there was a misconfiguration in the routing, and so even though the services as a group moved to another data center and they're all local, but one of them was configured to actually go to another region that didn't recognize that new zone, and so cross-region latency what killed the whole request. There is still a challenge with this approach of comparing two traces, and because they still could be outliers, so it's up to you to figure out what's the baseline, what to compare. And so that's why this kind of the last presentation that I have in this is another tool that compares a group of traces versus one trace. And the way we do that at Uber is that we have a test executor which generates synthetic traffic all the time and executes certain workflows against Uber architecture, simulating trips, essentially, like simulating rider, driver, matching, taking right? And so because that test, it executes a whole scenario, it knows when things go wrong, so it can tag it, and we get that as traces. And not only the whole execution is captured as traces, but we also get this strong signal of whether the trace is successful or not. And that allows us to aggregate the successful traces and build a statistical model of like what the normal execution of that workflow look like all the time, right? And it's dynamic. It's like the sliding window that if your architecture changes, for example, then the model will adjust itself. And then when the test executed detects a failure in the scenario, it also tags it in a trace, and we get another single trace which says it's a failure. And what we can do, we can compare them, the successful model and a trace. And notice that there is no choice of the human here anymore. You don't have to pick the baseline. It's all decided for you. The only thing you have to do is kind of attribute the failure by looking at the visualization. And visualization is similar to the previous one. We can see at the top is like the name of the operation. We can always go back to the original trace to drill down if we need to into specific details. But the main thing is that really it's a chronological sorted order and represented as a call graph. So it allows you to reason about what happened after what. And the color coding again is similar but slightly different. It's just like black means didn't happen, white means did happen as before, so all normal. The error note is really the some of the things that you will probably look immediately for. It's highlighted in red, and then if you click on it, you get like details on the right side as well, saying, oh, these are all the additional attributes that we capture in the trace, so you can get rich details. So that tool was used already for about a year or two, where it's very successful in kind of accelerating attribution of failures. And these are failures which are, even though there's a synthetic test failures, they represent the actual outages, because once that starts happening, we usually see, okay, well, yes, there's a particular city is having a bad day, right? Whereas another city may be perfectly fine. That's why we have the synthetic traffic, which tests like individual cities separately because of the different configurations. So in summary, the comparison views are very useful because, first of all, they surface a lot less information than you get from just a single trace. Single trace could be like millions of spans, overwhelming. And they emphasize the differences, so you even reduces information even further. You don't really focus on the things that are the same. You focus on the differences. And finally, depending on the use case, you may want to use different like actual visualizations, right? So at least different color coding is helpful in different situations. Whereas the second approach with the aggregation, the benefit of that approach is that it gives us a broader context. You don't have to pick what to compare. You can always be comparing outliers, but here the system decides what you should be comparing, and you just like deciding what's wrong in that comparison. And it's been very successful. Like we've had stories where people would look at the metric failure and say, okay, well, we spent 30 minutes trying to go through logs and all other tools, figuring out which service is actually misbehaving in the situation responsible to that alert. With this tool, they could have done it in 2 minutes. Just to take key takeaways from this talk is visualizations, as we've seen in the previous talk, are like exceptionally powerful tools for performance analysis and for outage resolution analysis. And tracing is kind of the fundamental backbone of how this whole thing is tied together. And so that's the end of my talk. Thank you.
Thank you very much, Yuri. First of all, public service announcement. There are spare chairs, so if you're standing and don't want to be standing, just seek out an empty spot. Sorry for the interruption. 2 questions for Yuri. Who'd like to start? Okay, over here, front row. I appreciate the wave. You'll get a mic. Hang on a sec.
Hi. Have you instrumented every single production box, production system? Because those metrics, it seems expensive in terms of performance to collect this much data. And I wonder, do you like instrument like 5% of your servers and use that as a...
So if you can instrument everything, I would recommend doing that. We have not because of performance concerns, but simply because of the nature of Uber evolution as an organization. There are so many services, frameworks, and languages being used. It's just not that easy to actually get instrumentation into every one of them. If we could, we would have, right? The way we deal with performance overhead is by sampling. So we're not collecting data on every single transaction. It's sampled heavily. Although the synthetic traffic that I mentioned, that's sampled 100%.
Thanks. Time for one more. Let me just look around. Okay, back there.
That was great. Do you run the synthetic traffic through your production systems, and then are there tools that can do this aggregate comparison that are out there that are open source?
So yes, the first question, yes, we do run synthetic traffic through production. It uses test accounts, but otherwise it's undistinguishable from normal production. Otherwise, we wouldn't be testing what's happening in the production. As far as the aggregation, I am not aware of the open source version. So the visualizations that you saw, they are actually open sourced in Jaeger, the trace differences available, but the actual aggregation, the last segment that I talked about, that's just because it's very tied to Uber, so it's not open source.
Awesome. Thank you for the questions. Thank you, Yuri.
Thank you.